This video is an introduction to precipitation reactions, and it will also go over some of the lab results for the lab where you try to determine solubility rules for different salts. So we're going to start with how precipitation reactions occur and why they occur on a conceptual level. So here we have a sodium chloride crystal lattice that is composed of sodium ions and chloride ions. And so this would be a tiny crystal of salt. And so we're going to take this solid sodium chloride and we can dissolve it in water. We'll put it in a beaker, we'll add some water, and we know it's soluble in water, so if we fill it up with water we can dissolve it. The molecular equation for the dissolution process that you see here is shown at the top. So sodium chloride solid goes to sodium chloride aqueous. The ionic equation would involve separating any aqueous electrolytes into their respective ions. And so we have sodium chloride solid, and we separate that into sodium +1 aqueous and chloride -1 aqueous. We add water, and then we know what happens eventually is they float separately. This is the reason why sodium chloride is an electrolyte. This is the reason why it conducts electricity, is because these ions are freely floating. They move around and can therefore conduct charges. We, on the other hand, take a different salt. This is silver nitrate. You can see here the silver ions. Silver cations are in a lattice with nitrate anions, NO3, with a -1 charge. So this is also soluble in water, and shown here is the molecular equation where the solid turns into the aqueous ions, and then we can separate the ions in an ionic equation where the solid stays together because it's together, and then the ions separate the way they would do in an aqueous solution. So if we add water to it, we know that these ions will separate from each other, and the ions will freely float around and move independently of each other. Now let's talk about precipitation reactions instead, because these are what we would call dissolution reactions, where we are dissolving a salt in water and the ions are separating because the water molecules are interacting with them. Now instead, precipitation reactions are sort of the opposite of a dissolution reaction. Instead of the ions separating, what happens is they come together and they form a solid when they were once aqueous. So it's very much the opposite of a dissolving or dissolution reaction. So if we take sodium chloride aqueous and we take a silver nitrate aqueous solution, let's say we mix them together in the same beaker. This is going to cause a precipitation reaction to occur, and the reason for that is because now we have these ions floating around separately from each other, and the problem with it is that silver chloride is very insoluble in water. It has a very low solubility in water. And so you would not be able to dissolve silver chloride and form a solution that had these concentrations. Because it has such low solubility, what happens is the opposite reaction occurs, and this is a precipitation reaction. So the silver ions that are shown sort of that dark grayish black color are going to float around. They are going to find the chloride ion and precipitate together. And they come together and coalesce, and they're going to form a solid that's going to float. This solid, what we call precipitate, which is abbreviated PPT. Sometimes we show an arrow going down. That means it's a solid that forms, and that's just sort of shorthand notation that sometimes people use in reactions, an arrow going down instead of the S. That's actually going to form the cloudiness that you see, and if you set the beaker or test tube or whatever on the counter and you walk away for an hour or so and you come back, it will have all settled at the bottom. So initially it just looks cloudy and milky, and then it settles at the bottom and is very clearly a solid suspended in the liquid. The sodium and the nitrate are what we call spectator ions, and they're called spectator ions because they don't really do anything. They're sort of like spectators at an athletic event, right? They just spectate. They're just watching. They're not really participating in what's happening. And so whenever you have ions that don't participate in the reaction that's occurring, then we just call those spectators. And those appear the same on the left side of the reaction as they do on the right side of the reaction. And we'll talk about that. So this is a picture of what's happening. You can see the milkiness that forms. That's the silver and the chloride coming together. Now, when you guys do the lab, you're supposed to sort of identify which of these salts precipitate in the presence of other salts. And that's going to help us identify what we call solubility rules that are going to help us determine the products of precipitation reactions, if any. So when you do this lab, what you discover, what you should have seen, is this, where the filled in dark spheres represent a precipitate and the clear colorless white spheres represent no precipitate. And so you would have done this on your 96 well plate and you would have identified, I don't know what your products are. I don't know what results you got. Sometimes people don't get the same results that they're supposed to, and typically the reason, I think, is because of contamination in some of the dropper bottles. So if somebody accidentally touches your dropper bottle to something else, then it's going to contaminate it. And sometimes just small amounts of contaminant can influence the results. This is what you should have seen, though. And so if we look at some common ideas here, one common theme is that I see an entire column here of no precipitate. And so this is going to be the creation of our first solubility rule. And that is going to be that ammonium ion, when it forms a salt, it always forms soluble salts. Now if we look for other really common ideas here, there's a couple right here. Sodium and potassium ion are both in the same family. They're both alkali metals. And that's going to lead to our second solubility rule, which is that states that salts formed by alkali metals are always soluble. All right, now we can see here a couple of our anions also always seem to form soluble salts. One of them is nitrate. So that's the third solubility rule. Salts formed from nitrate ion are always soluble. Salts formed from acetate ion are always soluble. So these are sort of four general solubility rules that are going to guide answers to questions that I will give you. And we'll do some practice problems. Now sometimes you can't really categorize something as an always or a never, but sometimes you can see usually, you could say usually. These are the four solubility rules I definitely want you to remember. Ammonium, alkali metals, nitrate, and acetate. They form soluble salts. If they are not one of those, you can assume that they are insoluble. However, you can see that carbonates are usually insoluble, right? That's a pretty clear message there. And we can say generally that silver and lead and mercury 1 tend to form insoluble salts unless they're combined with one of the always soluble cations or always soluble anions, right? If the counter ion is always soluble, that's the only case where you might see a soluble one. Now, obviously, there's some exceptions, like you can see silver sulfate, And another thing that we're going to learn second semester is that here we're categorizing things as it's soluble or it's not. Generally there's a range of solubilities, and so nothing's ever completely insoluble and nothing's ever completely soluble, right? So everything has a limit. And then here we can see that the alkaline earth metals, unless combined with carbonate, tend to be soluble, but not always. Now we're supposed to do some predictions in the second part of the lab. So we're going to base these on the solubility rules that we developed in the first part of the lab. So one solubility we saw is related to ammonium. I'm going to predict that all of the ammonium salts are going to be soluble. So I'm going to put S's here as my prediction. In addition to that, the alkali metals over here tend to form soluble salts. So I'm going to put soluble for all four of those salts. And let's see what else. I see nitrate down here. Oh, lithium, there's another alkali metal. Sorry, I forgot about that. Nitrate is soluble and acetate is soluble. So these are the ones that I'm going to put soluble, definitely soluble next to. And there are some that I could probably put in probably insoluble, like here, carbonates tend to be insoluble. And I think we decided that lead and mercury 1 tended to be insoluble. The other ones maybe, I don't know, that one's hard to guess. Maybe these are soluble because the other alkaline earth metals were usually soluble. And all the rest of these I'm just going to put question marks because I don't really know. So next we're going to look at some practice problems, and this will help you determine, you'll see how you're going to use these solubility rules. These were the results for part B that I got. They may not match yours, but this I think is what you're supposed to get. Okay, so here we have some practice problems. The accompanying photo shows the reaction between a solution of cadmium nitrate and one of sodium sulfide. What is the identity of the precipitate? What ions remain in solution? Write the net ionic equation for the reaction. So we're going to do problem 1 followed by problem 2. So we'll start with number 1. The accompanying photo shows a reaction between a solution of cadmium 2 nitrate and sodium sulfide. What is the identity of the precipitate? What ions remain in solution? Write the net ionic equation for the reaction. Okay, so here we have two solutions that you're mixing together. It's clearly a precipitation reaction because there is a precipitate that forms, which is the yellow solid that you see. And then the question is, what is the identity of that solid? So in order to figure that out, we have to write the two products that would form in a precipitation reaction, and then look at solubility rules and decide which one of them is not soluble, and that would be the answer to the first question. And then the one that's still soluble would be the answer to the second question, and then the ionic equation will do that last. Okay, so let's start with, we'll write the reaction. Cadmium nitrate and sodium sulfide. Those are the two reactants. We'll write those down. AQ just means aqueous. That's where you see solution. It should say aqueous solution. I should have written aqueous, but I didn't. Hopefully on future quizzes I will do that. You don't really know that water is the solvent in this case, but I guess generally you could assume that that's true, even though I didn't write aqueous. So in a precipitation reaction, what you do is you take the cation from one of the ionic compounds and you combine it with the anion from the other ionic compound. So you basically just swap partners here to form two new ionic compounds, cadmium sulfide and sodium nitrate. So we have cadmium sulfide and sodium nitrate is the other product. Now in this case, cadmium has a +2 charge, and I know that. I know it's cadmium 2 because 2 nitrates are required to balance the charge and make it 0 net charge. So when I combine cadmium with sulfide, I know that sulfide has a -2 overall charge because it's two columns away from noble gas configuration. It's below oxygen, and those group 6 elements tend to be -2 because they gain 2 electrons to be a noble gas configuration. So CDS, cadmium and sulfide combine 1 to 1. Sodium and nitrate, sodium is a +1 ion because it's an alkaline metal, it's in group 1. Nitrate is a -1 ion, and you know that just because you memorized the polyatomic ions. So those combine 1 to 1. And then you ask yourself, cadmium sulfide, is it soluble or not? And is sodium nitrate soluble? To answer that, we need to go to the solubility rules. And so there's a couple of solubility rules. The first one is that ammonium salts are always soluble, alkaline metal salts are always soluble, nitrate salts are always soluble, and acetate salts are always soluble. So cadmium sulfide is no, it is insoluble based on our rules. Sodium is in group 1A, and nitrate is rule number 3. So sodium nitrate is soluble, yes, for 2 reasons, the sodium and the nitrate. So for these, the identity of the precipitate is definitely cadmium sulfide. It's that yellow solid. And the ions that remain in solution would be sodium and nitrate. I separate them there as ions because the question specifically asks what ions remain in solution, not what compound is still soluble. Write the net ionic equation for the reaction. So down here we have the molecular equation, except I haven't balanced it yet. I need a 2 here in front of the sodium nitrate. And I need states of matter, that cadmium sulfide is a solid and that sodium nitrate is aqueous. So that's the molecular equation. The complete ionic equation, you would separate the aqueous electrolytes into ions. So cadmium and sulfate nitrate separate, sodium and sulfide separate, and you do that because they are aqueous. They are listed as aqueous and they're soluble, so they separate. Cadmium sulfide is a solid, however, so you keep that together, not separate, and then sodium and nitrate are separate. Now for the net ionic equation, you have to remove the spectator ions, which are the ions that look the same on the left and the right. I'm underlining them in red. You cross them off, and so for your net ionic equation, that's just cadmium plus sulfide reacts to form cadmium sulfide. So that's the net ionic equation. That's the only answer you need for that part. I wrote the other two just to lead into that question. Number two, we're going to predict the products of the following reaction. If no reaction occurs, write NR. So no reaction would mean that you don't form a solid. So if everything that forms is aqueous, you would write no reaction. So if all the salts that form when you swap partners are soluble, then you would write NR. For each reaction that does occur, instead of writing NR, you would write the molecular, complete, and net ionic equations and list all spectator ions. I think I forgot to list spectator ions. That's okay. All right, so let's start with the first one. Lead combines with iodide to form lead 2 iodide. Now here, I know that lead is lead 2 because there are 2 nitrates for every 1 lead ion. And so I know this is lead plus 2 ion, which means I need 2 iodides to balance that out. So it's PbI2. And then the potassium on the right-hand side combines with nitrate on the left-hand side in a 1-to-1 fashion, KNO3. Next, you ask if they're soluble. Lead iodide is not on our list. So you would say no, it is not soluble. Potassium nitrate is in 2 places on our list. Group 1A alkaline metal salts, that's potassium, and nitrate. So you would say yes. If either one of those were present, you would say yes. So the molecular equation, you just rewrite what's on the left. And what's on the right is PbI2 solid plus KNO3 aqueous, and then we need to add in stoichiometric coefficients to make it balanced. We need 2 Ki and 2 KNO3, and that should be balanced. Next, we need to write the complete ionic equation and then the net ionic equation. So the complete ionic equation, we separate all electrolytes into their separate ions. So lead nitrate will separate into 1 lead, Pb plus 2 aqueous, plus 2 nitrates, right? The 2 outside of the parentheses comes in front because you have 2 nitrates that are going to completely separate from the lead ion. So Pb plus 2 aqueous plus 2 NO3 minus aqueous. Next, we're going to separate potassium and iodide. There's 2 potassiums and 2 iodides. Last, we leave PbI2 together because it's a solid. And last, we separate the potassium and the nitrates from each other. These 2's come from the stoichiometric coefficient in front of the potassium nitrate. So you have to deal with the stoichiometric coefficients and whatever is in the parentheses, or whatever the subscript is after the parentheses. Now if we change this to net ionic equations, we're going to remove all these spectator ions that I'm underlining in red. So this part at the end where I wanted to list all spectator ions, I forgot to do that, but that would just be nitrate and potassium for this reaction. And for the net ionic equation, we're going to cross those spectator ions off. We're going to erase those. And now our net ionic equation here, I'm going to circle, is just lead 2 ion aqueous plus 2 iodide ions aqueous react to form lead 2 iodide solid. Next, we're going to move on to the second reaction. So here we're going to swap partners. Sodium combines with chloride, and ammonium combines with nitrate. Sodium chloride combines 1-to-1. Ammonium nitrate combines 1-to-1. Next, we have to ask if these are soluble. Sodium chloride is soluble because of group 1A alkaline metals are always soluble. So you would answer yes. Ammonium nitrate is soluble because the first rule is ammonium and the third rule is nitrate. For both of those reasons, or for either reason by itself, you would say yes. If you get both soluble salts forming, then the answer is no reaction. You're just going to mix these together and the ions are going to float around. They're not going to form a solid, which means there is basically nothing happening. They just float around. So this would be an NR